Okay, good morning, everybody. Starting our next day in this week 3 of our program. Once again, 2 talks in the morning and a discussion session after coffee break. And we are starting with Emil Bjerrum-Bohr from NBI telling us all about amplitude precision computations and fundamental gravity. The stage is yours.
Thank you. Thank you so much for letting me give this talk in this program. So my talk is titled Amplitude Precision Computation and Fundamental Gravity, because there's an interesting interplay about what we do with amplitudes, and especially our strive for computational precision, but also the fact that things has to be consistent. So when we compute things and we check that everything matches what we expect in the theory, we get into places where we see fundamental physics. So I'll try to outline some examples in computations that I've been involved in, where there's some interesting questions to follow up and see, and especially in the quantum regime. So we are all studying gravity here, and general relativity is a very beautiful theory of gravity. And although it's not quantum per se, it has still many interesting questions, and it opens up for interpretations in various directions. So one of the issues that we are studying astrophysically in these years are possibilities of extreme gravity, the kind of gravity we see when we have black hole singularities. But in relation to that, also possible quantum extensions, whatever goes beyond the expectations that we see from the GR would be interpreted in a quantum direction. And then when we come to the description of gravity, there's many different descriptions. There's geometrical descriptions that are associated with GR, but there's also these methods that use EFT and QFT flat space formulation, and somehow the language is very different, and we have to understand how to go back and forth. We are learning this. Then if we take serious, and I'll come to that gravity is an EFT, then there's various high derivative bounds, and we can question those from places in cosmology and astrophysics. We can also question graviton properties. So we traditionally assume it's a massless particle, but if it has a small mass, it has implications, and it can affect various cosmological models. And one question I'll get back to is this question of equivalence principle and quantum physics. There's also things, and that goes beyond what I'll talk today, about extra dimensions, supersymmetry, and string theory. So string theory is part of some of the computations that I do, because it's a very nice unifying model that you can go to understand various concepts you face in computation. But first, a little pitch for the current situation of data collection. So a few years ago now, it's actually not a new result, but at least 7 years old. But we have the first observation of binary black hole mergers. And when we analyze these templates, we get some data or direct access to gravitational interactions, and it's at very extreme regimes. So there's a lot of GR going into analyzing these things, but the amplitude fields set up to complement this conventional analysis. And there's still a need for theory to match the precision and the observational progress, because if we can analyze the spectra that we see observationally precisely, we can also see things that goes beyond our expectations, and that's where we can enter these extreme regimes. So people are looking at phenomenological questions like modified gravity, dark matter, all sorts of things in relation to the binary black mergers. And this is where we can use amplitude methods to refine computation and increase precision. And through these computations, since they are somehow mostly focused on classical gravity, we do have a potential to go into quantum gravity, because we can compute an order higher and we get quantum effects, and we can check that these effects are consistent with the theory, but also with the expectations from the classical theory. And then we can try to embed them in principle in such a theory. So just to give you the context of this particle physics version of gravity. So it's a little different from these lattice models. But in 1960s, Feynman, de Wit, and others set out to basically take the Einstein-Hilbert Lagrangian and treat it as you do for the other standard model theories. So you just derive vertices as you would do in any particle theory, and you compute Feynman diagrams. And it was actually taken into the gravitational wave community quite early by Kip Kovacs and Kip Thorne in 1977. A caveat is that it is not a very efficient way a priori to compute, because it uses a lot of off-shell things. So computationally, it was bad for many years, and therefore not necessarily a very viable path. And the reason for that is that gravity becomes a very non-abelian theory. It has lots and lots of self-interactions. So you have basically a Lagrangian that encounters enormous amount of self-corrections. If you analyze the coupling, you see it's non-renormalizable. So there's a famous paper by Toft and Veltman, 74. Basically, you cannot renormalize the pure theory. And if you include supersymmetry, you can't even remove all the UV divergences. So string theory was put in as a proposition of something that could by introducing a new length scale. But a slightly more practical viewpoint is that we just treat the quantization as an effective one. So we've seen that in various talks, but we start with Einstein-Hilbert and we include all the type of corrections we in principle could to that theory. It does limit predictability because we get more constants here. String theory would give us a specific effective gravity, but a generic effective gravity is a very broad theory. But what we'll see is it's consistent quantum gravity at low energies, at long distances. And basically this term here, that is not the effective one, has a huge validity for most of the things that we consider. So we can use that to work with gravity. So for people in the GR community, it's a natural generalization of Einstein. It's an ideal perturbative setup for the computations. And we can easily read off consequences of this theory and look at other theories like phenomenological, modified gravity theories, string theories, and supergravity theories. So, of course, we have to accept we have these high derivatives. We can, for a lot of consequences, like measurements and stuff, really ignore this since curvature is small. But there's growing interest in looking at bounds in theory. And I think one of the interesting thing about experiments like LISA, where you have long distances, is that you can actually probably there get to a point where you can start having some realistic bounds for high derivative operators. But the current two questions that we focus on is really doing these ultra precision tests of classical Einstein gravity. So we compute to high order, and I'll give some examples. And the other thing is to use this vehicle we have. We have a theory that includes quantum effects. And we could sort of think we could invent a low energy formalism for this. And this would be interesting, I think, for understanding how to work with quantum gravity, how to understand what happens with space-time and other things. So an interesting computation to start with, to see how this plays out, is to just start with the basic Einstein-Hilbert term. So, and we can include some scalar interactions. So we basically ignore all the higher derivative contributions to this order, and we can do that simply by power counting. The higher derivatives will give us extra factors. that are not yielding anything to the lowest order processes. And then if we write out the one loop, and this is something that I got involved in many years ago with John Donahue and others, we see that the type of diagrams are exactly like the ones you would have in other field theories. There's in gravity, you have to include all the different crossings, like you have in because there's an unorderedness. But you basically have a tree diagram with a simple one graviton exchange. You have boxes with two graviton exchanges, triangle with one massive line, and bubbles that have no propagating massive lines. So the interesting result is that you think that now you've done a effective field theory computation, this result might not be very interesting. It will have very few consequences, and they will all be tied to coefficients you don't know. But if you derive the result, you see that the two components that are interesting from the point of view of observations could be these long-range behavior, and they contain specifically no higher derivative contributions. You can see that the power counting allows beta 1 and beta 2 to have no effects from these higher derivative operators. So the only place it appears would be in a very short range behavior when you're very close to some singularity or something. But we can then focus on these pieces here, and we can then see that if we sum everything up, we get things that are consistent with GR. And we get a term here, which is the correction to GR. So the Newton term is here, a correction term to GR, and we get a quantum term here. What is interesting about the quantum term is that the quantum term has a certain uniqueness, but you can match up to what Einstein did, find the potential term in the Hamiltonian of Einstein, Infeld, Hoffman. You have to go through subtractions to get there, but you can do that consistently. So you can see that the result you get from the computation is consistent with what we know. But the quantum term is something new. It's something that's not in GR. And it's very logical to think about it as it is really an uncertainty of the distance integrated over this process of interaction. So if we have some distance 1 over r plus something of order h bar, we can Taylor expand it in this way. And we see to leading order, it's what we get from the classical, the 1. But to next order, we get an order higher with an h bar divided by an r. And that's exactly the type of term we see in the quantum. So the fact that in the EFT, we compute something which is a quantum effect, it's unique and universal because it doesn't depend on the higher derivative terms. It is actually a unique signature of having a quantum dimension to this theory. So it is worth studying how does this coefficient appear and how do we actually, in terms of the quantum theory, think about these distance measurements or how to think about putting in uncertainty in the theory. So that's what started me on this journey of thinking about quantum gravity. So to go back to the test of general relativity, so a lot of things has passed. Today we use something called the post-Minkowskian expansion of Einstein's general theory, because it's very useful for connecting with scattering amplitudes. That means that the results we have are valid for all energy regimes. We can make precision predictions also for high velocities as well as low velocities. And we can include, in principle, quantum and also the classical results. We mostly focus on the classical, but we do include quantum for physical consistencies, like seeing how the quantum terms appear in the theory. We take this approach, which was also the approach then, to work with very heavy fields. That means that actually the heavy fields are basically in a saddle point determined by equation of motions. And that means that black holes are just like scalar fields, point particle solutions in a quantum field theory. So we can, as an example of this, go back to the tree diagram and write it out. So the tree diagram has two black holes here, denoted by the two massive lines. The wiggly line is the graviton. When we sum everything up, we see we get Newton's law from the 1 over q that is Fourier transformed to 1 over r. We see, as we understood before, it doesn't give the post-Newtonian correction. It doesn't give you all the decorrection effects. But now, instead of having just the leading order result, we get relativistic factors in the results. So all the expressions we now have for the amplitudes are covariant, and we resum velocity contributions. So this we can directly read off from the amplitude itself. The post-Newtonian corrections, we have to analyze a little bit more. So we saw in the computation at one loop that they are sitting into diagrams with like two lines and like diagrams, for instance, with like this one, like triangles, where you have one line on one side and so forth. And you can have various different topologies. What happens is that in order to reach the classical limit consistent, you have to keep the wave number fixed. So when we integrate over momentum in these processes, it's a little counterintuitive, because you probably learned that when you do loop diagrams in the quantum theory, the loop order counts h bar, and that's true. But here there's two competing effects. There's h bar contributions when you have to reinstate. Yeah. So the graviton propagator is just when you expand the Einstein-Hilbert action to second order in the fields, and you have to pick some gauge. You get different propagators. I can show you some. There's some standard gauge fixing, and actually it's very much like a square of standard Yang-Mills Feynman gauge. So we can work off shell, we can work on shell. I will explain, there's some subtlety there, but the thing is, you go on shell, it actually is the gravitons that are on shell are very close to these long propagating fields that you're interested in. So exactly the contributions you see in the cuts are the one that correspond to the non-analytic pieces. While pieces that are a bit more like polynomial, they will not show up like that. They will show up exactly as things you don't see in the cut. But you could also do that from an off-shell formalism where you work out all the contributions. You just have more stuff you have to throw. But I'll get to the point of difference between on-shell and off-shell. But just to set the scene for how we count h bar in this. So normally we work in a place where h bar and speed of light is put to 1. When we reinstate h bar, we see that when we integrate, we keep wave number fixed, but momentum we count as h bar times wave number. So for massless propagators where scaling is uniform, we don't get h bar effects, but for the massive propagator where there's also a mass, we see that there's an extra h bar floating around. And when we expand the perturbative order and we analyze this, we see that actually the amplitude is a Laurent expansion in h bar. And we should expect at any given loop order to have terms of order L plus 1 in h bar. So when we compute these things, we actually want to compute the Laurent expansion in h bar, and then we want to take that result for the amplitude and make it consistent with, say, GR and other things. And there's a lot of subtle points here, but this is the setup. We even actually get terms in the amplitudes which we call superclassical because they come as inverse powers of h bar. And these terms have to be regulated away when we go to classical observables. But there's also pieces. I have not gone to the h bar linear order here, but there will be the piece that comes after the classical is, of course, the quantum effect to the amplitude. And sometimes we need that to guide us in our computations. So just to make a summary, the computational framework is, in order to compute everything, we have to go to all perturbative orders in principle. We have to retain, to test Einstein's theory, leading classical terms. These terms are interesting because they often are much simpler than we expect. Like we compute them and they look messy, but we can actually see that they have classical protection that makes them simpler. When we compute quantum effects, we need to go sub-leading from the classical. And that's usually much harder because we lose protection. But in principle, there's nothing in this method that doesn't allow us to do it. So we can analyze all these things in this theory. Now comes this story about the offshore gravity amplitudes. So in many of the first works in quantum gravity from a field theory perspective, people were using these vertices like this. This is DeWitt and Shannon. So this is 1967 and Shannon is from 80s. But this was the state of the art. There's like 45 terms here symmetrized. So you write it out on a computer, it's 100 terms. And for each vertex, you build a diagram, you have to take something like 100 times 100. It gets very, very bulky and tedious. And also, this is the first vertex in a series of vertices. So there's a 4 and a 5 and an endpoint vertex in principle. So these are the Feynman rules. Then you have contractions. Then you get the same type of factorial growth like you have in QCD. When you include loops, there's topologies, there's no ordering, there's lots of non-planarity. And the loop order leads to tensor integrals, which are complicated to reduce. So the off-shell way of doing things is just quite unpleasant. I mean, it's not impossible, but it's not easy. And this goes beyond what we see for gluons, which is already a hard problem at the LHC, where you have only 3 terms. For gravitons, it's about 100 terms. So we have a lot of gates dependent. So one of the key things to make progress was to use the same techniques we use for gluons, use spinor helicity to simplify. So the spinor helicity formalism is just representing the Lorentz group in a different way. Instead of using vector contractions, you use spinor contractions. That means you can write out dot products as spinor products, but now you have the advantage that it factorizes in 2 parts, holomorphic and anti-holomorphic spinors. And you can even build expressions with polarization tensors like gravitons, because you can use this efficient formalism of using spinor helicity polarizations. So by that, if we go back, so one more thing. So people also in the 80s saw Park and Taylor, Behrens, Giele, that amplitudes expressed in this formalism have special properties. They are simpler. So we have these MXV amplitudes. And in particular, the endpoint amplitude is very simple. It's 1 term to all orders. So basically, we get a huge perturbative resummation. So just as an example, for the 3-point vertex, we put in spinor helicity. We can reduce this whole ugly thing to a simple spinor expression like this, which is a simple term instead of these 100 things here. So it just means we have eliminated the off-shell degrees of freedom and we only count the on-shell. That means we have to collect the information we want from unitarity cuts, but there's no loss of the important information there. Then we also take into account string theory. So string theory gives us compact expressions where channels are added instead of having Feynman diagrams with separate poles. And we can even use the Cavalli-Valentine relation to decompose closed string into open, and that means that we can use that to recycle Yang-Mills results into gravity results. So the whole question of generating trees with high multiplicities of gravitons is actually solved. We can do that to very high order. Here's an example of an n-point graviton tree, which uses the Behrens-Thiele recursion formula. And we can write that in one page. That's quite a big achievement compared to these very complicated Feynman rules. Then finally, since we are working with trees which have unshelled states, we have to use cuts. So in the cuts, we just put in trees. We sum over all the unshelled states in the cut. And we use a special cut integral here. So what we do is we write out a basis for the amplitude, and then we match it to the cut contributions. But if we can put in simpler graviton trees, and we can even have some structure in this, we can make these loop amplitudes much simpler. And then we can put in all sorts of matter in the cut. We can work with various supersymmetric models and so forth. So, and as another example of how we can do these type of computations, I'll then focus on a result we did with massless matter. So after doing scalar scattering, the mass, we thought that it's an interesting example of looking at the scattering of massless matter. And it ties very well down to the very famous Einstein bending angle, which is the important test of GR from 1917. And it has interesting features because in this calculation, you have massless external fields. So that means you have higher singularities associated with these fields. And when you have massless fields, you also have intricate consistency procedures to account for how these singularities becomes regulated. And then as a further thing that we thought was interesting is what happens to the quantum effects if you do that. Is it still like universal, or is there some difference when you consider quantum? So the standard setup is, as I outlined, you write a Lagrangian, and you can write that as broad as you want. It should include the Einstein-Hilbert term. It should include the model term. And in principle, it should include the effective operators just for show. Then you analyze, and you see what you need to retain. So in these cases, if you want to look at scalars, you put in the scalar Lagrangian to leading order. If you want to put a fermion term, you take the the fermion Lagrangian, but you make it covariant. And the same thing you can do for photons like this. So you can have 3 different Lagrangians, and you can put them into your gravity model. Now you want to do this in terms of cuts. You write down the cuts with the 2 trees. So you have to identify the true tree components you have in this case. And in this case, when you write it out, you have the special phase space integrals, the 2 trees. Across here is the gravitons where you sum over the helicity states. All the external particles, of course, this is, say, a massive black hole, and this side is this massless matter, for instance, a photon or massless graviton like a neutrino and so forth. And in here, we have the gravitons that we sum over and the cuts. Though for the trees written out in terms of spinor helicity, the expressions are really simple. You have all the propagators collected down here. And at the top, you have the numerator factor that describes the particles. So being on the cut and allowing these spinor helicity expressions makes actually things very organized and simple and simplifies this computation. Then when you write everything out, you see that all the denominators have same factor, but the numerators differ between the different fields. But there's some systematics in this. You see here you get terms traces to fourth order. Here you get traces to third order times something additional. And if you go to the photon case, you get a first order trace times this trace squared. So there's a very organized pattern that you can follow that simplify the analysis. So then you consider the cut. You write down the integrals that occur in the cut, and you identify the various functions. You see there's various coefficients you can fix right away. And then there's these additional bubble coefficients, the B, U, X, and they are actually different for the different matter fields. So once you put in the integrals, take the limit, you see you get logs, you get 1 over q squared, you get 1 over q, so this is post-Newtonian. Logs are quantum and have h bar factor. There's some phase factors in here, and there's a cutoff scale in mu because we have these massless fields. There's also the cutoff scale in the big mass here, which is the m sitting there. So in order to go to an angle, we had to go through a iconal approximation. But once you've done that, you see that actually it spits out the right Einstein bending angle. And not only that, it gives you the second order, the 15 over 4, which is Einstein's correction to the leading order in B when you look at the bending angle. But if you analyze the quantum effects, there's also a piece of magnitude this, where these coefficients are actually not the same across fields, they differ. So the universality that we saw for the classical theory is somehow not retained in the quantum. So this is, I mean, it's a unique effect. It's a different, and it's a break with classical universality in gravity. So a caveat here is, of course, that doing something like bending of light would be very hard to measure. But in principle, it's a tabletop experiment that is waiting to be done, and where somehow we could try to see effects of gravity in this theory. Which one?
At zero. Okay, log p over 2 and 0.
R0 is related to this cutoff scale you put for the infrared. So it's in principle, this coefficient is not totally fixed. You need to fix that from, say, a measurement or a high order. I think that's what we discussed yesterday. Some part of it is finite and some part is not. But this is equivalent to what you have in QCD, where you compute some cross section, and there might be some scale parameter you cannot compute, but you can fix it from other constraints in the scattering process. It's a cutoff, so it is basically not a physical quantity. There should be some way of figuring out. There's some piece there that is related to how you have done your cutoff of your experiment. But in principle, the result itself is done on shell, and it comes from infrared divergences. Yeah.
Always very small, or for some different energy scales, it could actually make it quite.
We looked at that. I mean, it doesn't look like any of this will scale in a good way with energy, but you could hope to have something like this. I mean, we did speculate things like equivalence principle. I mean, it's a very broadly formulated thing, the equivalence principle. So you can both say you break it and you don't break it at the same time, depending on which formulation you want to pick. It could be interesting to follow up on these things. I mean, this was just to try to outline how this computation could be done in principle to leading order. But I mean, the fermions we have massless are basically neutrinos, and we have a lot of those. So it could be an interesting question to look at. But still, quantum effects are suppressed around 40 orders of magnitude compared to classical. So you're up against really deep wall. Yeah. So that's why actually looking at another scenario where you look at black hole dynamics is in some sense is better, because here you have much stronger fields, and in some sense if you have something quantum, there's a bigger chance for something to show up. Yeah. So that's another thing one should check. I mean, in this, we didn't include the higher order terms, but the higher terms will give you higher derivatives. So in principle, they will not, to this order, give you long range effect. But you have to go to some loop level order where the higher derivative terms in principle could play into something of order of magnitude with the classical. I think you have to go to 4 or 5 loops to start having some effect. There has been some papers on R cubed, I think, in black holes, and I think it's at that order of magnitude you have to. But it's something people are looking at in the experimental data, because data there will actually, if somehow it doesn't follow Einstein, and there's an excess of something, signal that there might be some extra attraction, and then high derivative corrections would be a very natural place to go. So I think there's bigger chance of probably finding something like this than a real quantum effect, and it would at least validate our effect in the gravity. So if we do spinless gravity from quantum field theory, it's very much the same setup as we did for the massless field. It's very much the same setup as we did in the first one loop computation. But it's a little bit more systematic in the sense that we're using on-shell amplitudes all the way. We are also making sure that everything is post-Minkowskian, so every relativistic effect is kept. We use the double copy or KLC property to make these trees recycled from Yang-Mills. So we have very good compact trees we can put in. We use the on-shell amplitude techniques to simplify. And again, since we can focus on long-range behavior for classical effects and sub-leading quantum, we use unitary cuts to capture everything. So one thing we have to face when we link to Einstein's theory is that we have to also face how to go from an amplitude itself to an interaction potential. And these things are not the same. If we go to non-relativistic quantum mechanics, it's a little easier to analyze. And then once you understand it there, you can go back and generalize to a relativistic case. In most instances in these analyses where you construct a potential, you just restrict yourself to classical objects that scatter classical distance scales. So you write down a Hamiltonian, and for relativistic physics, you can work with this, like the Salpeter equation, and you want to determine V. And then when you look at the Feynman diagrams or the amplitude, often you have included in that terms that you don't want, like annihilation channels and other things. We have to exclude those from the computation. Basically, we remove some of the channels. And this setup allows us to work directly with perturbation theory in the context of amplitude. Then when we analyze in the non-relativistic limit, we can define the potential as basically, to leading order, the Fourier transform of the Q potential. So what we compute in the amplitude, we can basically just Fourier transform and we get the R potential like we did it at one loop. If we are considering this and going to higher orders, we actually have to work with the extension given by Lippmann-Schwinger. So it means that the amplitude is equal to the potential, but plus a term here, which is called the iteration. So basically it signals that we are rewriting our amplitudes in context of a quantum mechanical system where we have a potential. So there's a difference in energy between states, and there's a propagation in energy that we have to correct for. So the amplitude here is equal to V, but times this iterator here, where how we define basically the coordinates in V depends on how we do this iteration. So M here is always the amplitude, but V has some choice of coordinates associated. So then we can focus on the amplitude in order to compute things. So we start with, at one loop, writing out the amplitude. This is the same computation as the first one, but now done post-Minkowskian. So we get a box, we get triangles, and we get bubbles. One way to simplify this is to basically put everything in a scalar integral basis. Then we have to isolate the coefficients. And we write out the amplitude in terms of a Lorentz expansion. So we order each order in h bar separately. So we see the box comes with a term that follows an h bar to the -2 and to h bar to the -1. There's a box and a triangle contribution, and so forth all the way down to h bar to the 0. Now, if we write out the integrals and we combine things, we see that in the one loop, the box and the cross box are very similar, except for a phase that comes into the box. The triangle comes out to leading order just being the 1/q term. But in the box, there's these pieces here that depend on d, and there's a logarithm. So these coefficients are what we get from the unitarity plot. But we have to compute that iterator that we see up here, the one that is described by the Lippmann swinger. So we compute the iterator, and we have to add that to the result. And that removes from the one loop the piece that comes with the pole in 3 minus d and the log, and simplifies the result. And this allows us to extract the second order potential in this theory. So it's not just the Fourier transform, it's the Fourier transform to leading order plus an iterator that removes certain singular pieces from the amplitude. And it's very reassuring to see that this very precise procedure following Lippmann swinger matches what is done in other papers like Bern, where they have some other subtraction scheme for these things. But the main effect is that things that are singular in the amplitude are necessary, but they're removed when we go to physical potentials and observables. So now, after summing everything, we get the amplitude. And what we have learned is that in order to go to classical physics, we have things like choices of coordinates and subtractions to worry about. But an empirical understanding is that a lot of the information we have in this is really given by the two coefficients of the triangles here. So the two pieces that has just one massive propagator on either side, and these two coefficients here are the pieces that gives us the real physical observables or the interesting physical information. The rest is just there for consistency. And if we keep everything, take the classical piece, it gives us this piece here. And if we go one step higher and include the quantum, we get this piece here. And as I will get to when we get to two loop, this is important for actually how to rewrite gravity in terms of an iconal. So lessons from the one loop is that only part of the amplitudes are really important for observables. There's part of the amplitude which is there to be subtracted for matching with consistency. And at two loop, it becomes even more evident what's going on. So at two loop, you can follow exactly the same setup, where you now have 3 gravitons propagating. So the cut is a bit more complicated. Now it involves 3 integrations here. There's a delta function. And still, the setup of doing the integration is the same because you go through figuring out a basis for your integrals, use unitarity to fix coefficients. There's a new effect that you have to include self-energy. So you have to take the one loop and you have to make it self-interact across the external lines. So from the cut alone, you get a piece that gives you part of the result, but you have to include these self-energy contributions like these ones. And for the different types of topologies you have at the classical, it's relatively simple. It's like the one loop iterated, but it's still more complicated to compute these things. And Paulo here did a lot of work with his collaborators as well. So this was a number of groups that were actually working these things out and comparing very carefully in order to get to results. Which one? I think you have quartic here. Like you mean this is, but this one here, in principle, you could join this line here. So you could have something which is a 5-point. It's a graviton, but these are master integrals. So these show the propagating lines. But in the actual computations, you could have something canceling that propagator. And so you resum in a basis that has all the propagators, and then you put some coefficients in front and you integrate. But it's, I mean, as you go up, you have more. But also when you do the cut, these are amplitudes. So the amplitudes you put here would have 5 legs. So you have to account for the multiplicity, but it's accounted for very easily in the setup we have. I mean, we can scale the multiplicity very easily. Yeah. So this is the result at 2 loop from the cut. And one sees that it has an imaginary component. So this is associated with the fact that, so we have to, again, write out the amplitude in terms of orders of h bar in Lorentz expansion. And then you see that actually the imaginary contribution is cancelled by radiative contributions. So you can see that better when you go to B space. So what is interesting now is that you see very clearly that the amplitude have an iterated structure if you Fourier transform from Q space to B space. So when you go to B space, you see that the various components in these amplitudes satisfy these equations here, where the order h bar to the -3 is actually the cube of the amplitude piece with the -1. And so forth. And you see the quantum pieces appear as well. So there's classical. These are all classical, but the quantum pieces appear, for instance, up here. And this allows you to write the amplitude down in this form here, where you have the amplitude in B space times summed over number of loops plus 1. As a phase factor here, where the quantum appears in the delta, and an exponential, which is these phase shifts that are purely classical. And the 2-loop order, what you read off is this formula where the quantum piece here, the delta 1, goes into this piece here, which is the prefactor of the icon. So what you need the quantum pieces in all this for is actually for reconstructing the iconal in a consistent way and extracting what is classical physics in this amplitude. So the quantum physics has actually an importance here for consistency. If you put all diagrams, it's a good question when that appeared. In the prefactor, yes. But they will be associated again with the higher derivative contribution. But it's an interesting question. What happens if you now take the full EFT approach and rewrite the iconal? But the iconal seems to be the optimal framework for doing this. And it actually clearly separates quantum from classical, because the classical, the phase shifts associated here, are really the stationary state solutions on the massive lines, while the quantum pieces here are associated with that extra uncertainty you have in the amplitude, and it's clearly separated in these factors. So you can then go to J space from B space, and you get the scattering angle out, and the scattering angle is, of course, matching all the expectations, including Paulo's paper, which was very influential for getting all these things correct. So it's a very nice result where you actually have computed everything, even the quantum corrections, and you have seen exactly how the iconal appears. And in principle, we should understand how to do this to all orders, including these higher derivative corrections, to see how this will play out with UV and everything. But it's a very nice way to work with gravity and have a connection to GR, which is demonstrated. And these angles, they play a big role because they go into the template generation at the LIGO. So when you write these templates down, you use these banding angles that you get from these computations to construct an effective potential, and that gives you things like in spiral and all the data from LIGO. So if you get this wrong and you don't match LIGO, there's a problem. And if you get it right and there's an excess at LIGO, then you have something to look for in your theory. So basically the tools here were for going up in loops, the on-shell integral construction, multi-loop integration, and these recent techniques by Smirnov and others by integration by regions and using PDE approaches. So far in all this, focus has been a lot on classical precision physics, but there's nothing in this that is not sort of allowing you to take into the sub-leading as well, and you can compute quantum terms. It's just tiny effects, and it's not like at the moment possible to observe. I think the interesting question is more on making a quantum interpretation. So the classical physics we understand really well from going to the classical limit, from seeing that these classical terms match things that come from equation of motion, but we lack a good framework for the quantum effects. So what we have to do is maybe make some models where we can see what happens to the parts of the scattering that is not associated with this stationary state solution. We have also used all of our amplitude toolbox, meaning the double copy, unitarity, spinor helicity. I didn't explain the CHY formalism, but that's what allows us to go to very high multiplicities with very ease. And string theory is a very nice guide for doing this, because we could even, I mean, Paulo's an expert on this, but we can work in string theory and compute amplitudes there to a great deal extent. And we can learn a lot about how we extend to various scenarios of external particles. So for the gravitational wave community, the interesting things are to use these techniques to go further. It is a problem to go up in loops. To focus on quantum effects is more like a theoretical thing. If we want to consider things to do with regards to this field, I mean, things like radiation, validity of the exponentiation, validity of the amplitude at high energy, UV terms are open questions. Quantum terms are not really been approached a lot. Higher curvature terms, there's some papers, but it's still a very open field. If we have things that are finite size, like not black holes, but neutron stars, there's also another theme to explore, where you use effective field theory to describe the finite size. We can use string theory, geometric approaches, like there's a lot of amplitude twister technology we haven't used. And spin is a very hot topic because the actual black holes that we scatter are spinning. And we can get interesting stuff studying quantum physics, so higher quantum spin, and extracting the classical from these amplitudes. So a recent result that we are working on is to compute the Compton amplitude, the input amplitude you need in these unitarity cuts. Start with something that is based on a quantum field theory bootstrap, but derive the classical spinning amplitude from that, and especially the classical results. But then it also opens up for doing this with quantum corrections and looking at consistency, like how does the iconal exponentiation work in this case. So I hope I've convinced you that there's also interesting perspectives in working in perturbative quantum field theory, and in particular, an interesting question is to give a physical meaning to quantum effects here, and to have a framework for working with these things. And we can easily do computations here. The problem is to come up with formalisms that are useful for this. And the iconal has been a very useful concept so far, but we probably need to extend that to go truly into the quantum regime. So thank you. Yeah.
Thanks a lot. Yeah.
It's very impressive, the simplifications.
Yeah.
Flat space. Is there any analog of that might apply to curved space geometry, such as, for example, the sitter?
So people are looking at these things. I mean, you don't have to work actually. I mean, we've progressed from spinalizity into something I would say like just a covariant formalism. So you can actually also in the cut work with covariant objects. And there, I think there's no limitations on what type of background you have. So you could have. Yeah. I mean, I haven't studied that. I mean, I have been looking at non-trivial backgrounds, and in principle, if you work in a non-trivial curved background general, you can describe certain things also perturbatively around that. So people are looking at things that, for instance, free some weird backgrounds in the classical and deriving perturbative consequences there. But in the sitter, probably it requires some additional technology. Yeah, I don't know.
Roberto?
Yeah.
So in one of the stuff, you said that the quantum predictions, the potential can be interpreted as effect on the corrections to the measurement of distance.
Yeah, yeah.
And then you would say that you project expanded.
Yeah.
So does it mean that you expect the next order in 1/r to have the same coefficient, 41 over 10?
No, I think it's. I mean, I think you have to integrate over. I mean, there's a lot of places in these diagrams where you have some measurement, like there could be some uncertainty, and you have also many different propagating. It's more like an argument for why it's natural to have something like an H bar leading effect, even though you could have a classical theory where you have a 1/r. So, but there's some connections when you actually do computations between one loop and two loop. You do see some pieces being iterated, but then there's also pieces that are not iterated. But it's an interesting thing to maybe work out sub-leading quantum corrections at one loop, two loop, and see how much, if there's some pieces that maybe is transferred across. But in this structure of the iterations, there's definitely something that factorizes in interesting ways. So yeah, but it's not to be taken too serious as a physical tool, more like an explanation for why it's natural to have something like a a quantum correction in the amplitude. Yeah.
Very brief question, and then we have to continue.
Okay, so one of the big problems generalizing what you're doing to cosmology is these identities that John Donahue and collaborators have derived first. The things that take the general, say, 4-point box diagram and express it, or express the part that would be the logarithm of q and the square root of q squared.
Yeah.
Terms. To understand physically what those identities are expressing, it would help in trying to generalize those to curved space backgrounds if we could get some kind of physical. I mean, the way they were derived was you just do the integral and you look for the non-analytic part.
Yeah, yeah.
Dependence in the exchange momentum, but of course you can't do that.
Yeah.
Consider, is there some way of expressing physically what those identities are doing, the things that tell you, the important parts of the diagram for long-range scattering?
So you're talking about these identities in the original paper where you have different pieces in the vertex operator, or?
No identities for the loop diagram. So in your paper on electrodynamics,
Yeah.
in your appendix, you had a series of identities
Yeah.
that you checked and that John had originally derived.
Yeah.
Collaborators.
Yeah.
That give the logarithm, the square root of q squared, the logarithm of q squared, etc. Terms. Those were derived by just taking the loop amplitude, doing the integral, and then expanding it.
Yeah.
Is there? But we can't do that with the sitter. Is there some way of expressing physically what those things are telling you that we might be able to generalize to cosmology?
I mean, I think what they do tell you is the counting of h bar actually, but what is intricate is that you can have expressions that somehow are counterintuitive, or it's complicated to see the logic. But one could try to analyze. I mean, the modern way of doing these things is to basically let a computer suss out the various integrals that you need, and maybe you could do something similar in this. But I mean, I don't know what would be required if you say you can't do a perturbative field. It's hard to maybe do things, but maybe you don't need a fully consistent S matrix there. Maybe you could still focus on some pieces that matter to long range propagation. I'm not sure, but maybe we can discuss that. Yeah.
Yeah, we have to continue, so let's thank Emil again.
Okay.